Okay. All right. Hello to the 8th lecture in mathematical finance. So the main task for today is to study the binomial model and the pricing and replicating of financial options in this very fairly simple context. But just to make one remark before I start with the binomial model. Last time I was struggling with the last proof. So the reason why I was struggling was because, okay, there was missing a condition in the proposition. So I updated the lecture notes, and then the proof works exactly as I presented it. I will add some details in the proof itself. So if you still feel like, okay, the proof was not 100% clear, please check the proposition and its proof in the lecture notes. Again, I will add there, as I said, details so that it should be clear for everyone how it works. And I also updated a bit already or corrected the lecture notes I made during the last lecture. All right, but I don't want to spend too much time on it because I want to focus today on the binomial model. And this brings us directly to the next chapter. This is chapter 3.2 is the binomial model. And actually, I only want to consider it at the beginning with one trading period. So we make it even simpler. Probably this is the most simple model one could think of, but as we see during this lecture and then understand during the course, is that you can make many very deep and important observations in this simple context. And then we tried later on to understand how this simple observation or simple but deep observation transfer into the general context. So this model was mainly introduced and studied by Cox, Ross, and Rubinstein. So this is why it's also called the CRR model, as it was introduced by, as I said, Cox, Ross, Rubinstein, and their motivation to study this model was actually to approximate the continuous time mathematical framework with a numerical tractable discrete time version. But this is what we see at probably the very last lecture, that these discrete time models, so these binomial discrete time models, if we choose the parameter in the right way, converge to the continuous time world, namely the Black-Scholes model. This is just to give you an idea what we will see later on. All right, so let us start by setting up the model. So here, let's let's call it the model. Binomial model. So we want to use a probabilistic model. This means we want to start with the probability space on omega f p. And here we want to make it rather concrete. So our sample space omega is just given by two elements, either u or d, which will correspond to our prices going up or going down. Here, well, since this is a finite set, we can take the sigma algebra on this probability space as the power set, and the probabilities of u, so that u appears, is given by a small number p, which is between 0 and 1. And so that we'll have really a random object, we want that p is strictly between 1 and 0. All right. And this is our probabilistic basis, and now we want to put the model on it itself. So financial market is now given by our bond, denoted by B, and the price process of the risky asset, denoted by S as usual. And we want to have only one step to make our life as simple as possible. So we have only one trading period. And what we will think of, just to clarify it, so the time 0 is currently where we are, and the terminal time is equal to 1 is somehow the future. Okay, right. So this is the idea. So currently we observe the price at time 0. So these are deterministic constants, and the future prices are random objects because we can't forecast the future. Okay, so that's so we have these two prices. So the risk-free one, B, starts at 1 as usual, so we normalize it to 1, and B at time 1 is just given by 1 plus R, which is sum of the bank account, with our interest rate here being strictly bigger than -1. So this is the risk-free asset. And then we have the risky asset. So this starts again with the constant because we observe the current prices. So we assume it's a real number, and we assume that's positive because it's rather natural to assume positive prices. And then we have here S1. And this depends on the random outcome on our probability space. So either the price goes up by u. This happens if omega is equal to u, or the price goes down by d if omega is equal to d. Okay, now we just need to specify u and d. So they are strictly positive constants because we want that the prices stay positive. And so this here is our risky asset. This is exactly the language we have used before. So that's our model. And one last thing we usually want to fix is namely the filtration. And here the filtration is rather simple. So of the filtration. Right, this is now just, I mean, we have just time 0 and 1 is given by, so well, since we have constants at time 0, the filtration is given by the trivial one, and at time 1, and we always wanted that the filtration at the terminal times equal to the sigma algebra on the probability space. So this is what we have here as well, and this means just the power set of the set omega. Okay, so that's our model, and now we can come back to, I mean, how the trading strategy looks like. I mean, we have introduced last time how we allow to trade on such a discrete time financial market, and we agreed on that we want to trade in a predictable manner, and we agreed on that we want to trade usually self-financing, right? We are not willing to throw away or add money. Multiple time steps for this were all stochastic processes, but here, agreeing on this binomial model and with one trading period, the self-financing trading strategies are just real numbers, right? So here, self-financing, trading strategy is just a pair consisting of a number beta and alpha in R2, right? So you can check, I mean, that this is exactly what the definitions from last lecture give us in this setting, right? Because I mean, just one time step, and the filtration at time 0 is, so this pair has to be measurable with respect to f0, and f0 is the trivial sigma algebra, so they have to be constant. And this is more to recall it. So beta is the number of the risk-free asset which we hold. Right. So what we do is at time 0, we buy beta shares of the bond, and alpha shares of shares shares on the risk key asset. All right. That's, I mean, this turns all the mathematics into a rather simple framework. And finally, a remark how simple this setting looks like here is, if I consider now the value process corresponding to such a simple trading strategy, oh, 0 to 1. So this is the value process with respect to the trading strategy phi, which is as usually given by beta alpha. And well, we can easily calculate it because here it's now just given by alpha times the price at time t multiplied with beta price, plus beta times the bond for here t in our index set, which is just 0 and 1. Okay. So all the complex mathematics we have developed for stochastic processes are actually not really important in this one-step setting, but of course later on we want to understand the more complex one, so meaning multiple time steps and more complex models. Okay. Okay, so let's come to our first goal. And this is for, if we consider a financial model for a market, then the first thing we want to ensure that this model is somewhat realistic, and we agreed on realistic means for us that it fulfills the no arbitrage principles. So this is first aim for today is to ensure that our binomial model here as B fulfill the no arbitrage principle. Right. So what we have to do is, of course, we have to check that there's unlimited liquidity, but this is, I mean, as before, I mean, this is basically done by the market. So we just have specified the price for one quantity, and we are not making any restriction how much we can buy or sell. We have a linear pricing rule where we have no trading constraints and so on. And the information here is given by the random variable S1 and S0. So there's all the information is all available and all reflected by the prices. So the market efficient market hypothesis is also fulfilled. So the only assumption where we need to be careful is the assumption of no arbitrage. Right? So we need to ensure, this is the main task, that the binomial model is arbitrage free. And this is, I mean, this is might be not right, because this might depend, this is what we see, and it will depend on the parameters we have here in the model, right? So we have here parameter R and the parameter U and D. And well, if the market is arbitrage free or not will depend on how we choose these parameters. Okay. So the first task for today is to understand under what condition is this binomial model arbitrage free. And this is the content of the next lemma. Just 3.7. So what we consider is the binomial model. So model, and we are talking here about the one-step market. So 0, 1. We observe the following equivalent conditions. So we get an equivalent characterization when this binomial model is indeed arbitrage free. Okay. So the first one is, okay, we want to characterize when this market is arbitrage free. Right. The second one is we know that it's arbitrage free if U is strictly bigger than 1 plus R is strictly bigger than D. And I forgot to introduce the following parameter. Okay, this is not part of the so as you see here, the 1 plus R plays an important role. So let me make this to definition. So this is 1 plus R is just given by this capital R here. And the last equivalent characterization of the binomial model being arbitrage free is that there exists Q, which corresponds to another probability. So it's a number between 0 and 1, such that as 0, so the price of the risky asset at time 0 is equal to 1 over R Q U plus 1 minus Q. D. Right. And this is, okay, can be written, I think, more nicely as a conditional expectation of the price process divided by R. And now, what is this Q here? So Q, Q is another probability measure. Such that the probability of S1 being equal to U as 0 is equal to Q. So what we do here is with this number Q is we assign the movements of the risky asset new probabilities, right? So we change the probability on the underlying measurable space. So we replace the measure P by another measure Q. Okay. So this is the first thing we want to prove today. Okay. Let's come to the proof. And just, before I start the proof, here you see, so what we want to do is first we have to prove all the implications here. So we start with no arbitrage implies these conditions on the parameters. This is, as you probably will not be surprised, is okay. The the property of the market's binomial model to be arbitrage free depends on the choice of parameters. And this is okay. We first want to show if the market is arbitrage free, then these parameters fulfill these two inequalities. And the way to do this, I mean, this we have seen already a few times, is okay, we want to assume that this is, so I is not true, and then we want to show that there's an arbitrage. So this is the usual trick of applying a proof by contra positive. Okay. First case, let's assume that, well, the second inequality is not true. So let's assume that D is bigger than R, which was 1 plus R. And given this assumption, we want to construct an arbitrage. Well, so how do we make an arbitrage? So we have two trading periods. So at time t equal to 0, how do we trade? Well, we borrow, right? Right. I mean, with this assumption, we know that the evolution of the risky asset is always better than the evolution in the risk-free asset. So what we do is we go to the bank, we borrow as 0 so that we can afford to buy a risky asset. So go to our bank account, we borrow it there, and we buy the risky asset. So now with our notation, we can write this mathematically very simple. So this means we take our trading strategy phi, which is minus at 0. So this is the position we have in the bank account, and one risky asset. And now we wait until time 1 appears. So we wait until t is equal to 1. And what does it mean? What is this, our value or capital at time 1 now? If we follow this trading strategy, well, we can now, I mean, this is a random variable, but we can estimate it from below by the worst case, namely, okay, and this is the money we have in the bank account. So, bank. Plus d 0. So this is the worst case we have in the risky asset. So. Yeah, because I mean the upwards movement u is assumed to be strictly bigger than d, so this is even better for us. So the downward movement is the worst case, but now by the assumption we have made here, right? We know that this is strictly positive. So this means this gives us an arbitrage. Right? We start with 0 capital and we make surely some money. Okay. Worst case, now, well, there are two inequalities which might be not true. So the second case is we assume u is strictly less than r. And well, you can repeat the argument by just swapping your positions and you get, again, an arbitrage. So you sell one risky asset, so short selling is allowed, and you put the rest in the bank account. All right. So I'm not redoing this for the second case because the ideas are exactly the same. All right. So next, we want to prove that the property II implies the property III, right? So let us recall what we want to prove. So we want to prove if the parameters fulfill this inequality here in II, so that U is strictly bigger than R plus 1 is strictly bigger than D, and then we can define such a Q so that the S0 is given by this conditional by this expectation. So I keep here the proof short, but by just giving you the how we choose Q. And you might wonder, okay, well, why do I have the idea to choose this Q? I mean, I will check now that this Q works, but it somehow pops out of the air. But I think at the end of the lecture, or I hope at the end of the lecture, it will be clear where it's coming from. So we will basically derive it again in the first time here in the case where we in the next half hour. So, right, and this is well, if we define this Q like this is a number between 0 and 1, well, because of the assumption we made in 2i's. And this means if we choose Q equal to this, 1 minus Q is equal to, so now we plug in definition. So that's minus D plus R, right? This is just putting in the definition of Q here. And now we can, well, make this right, so the D is canceling. We have U minus R divided by U minus D. Okay. It's nice. And now we want to check that the claim quality here holds true, right? There's the second one here. So this here is just the definition of the expected value, right? Let me change the color. Oh. So here, there's nothing to prove. Because this is just the definition of Q, right? This is a expected value on a probability space with 2 elements, so there's nothing to do. So we want to check the first one. Proof. And this is what we're going to do here, is taking this Q, which I just gave you, and checking that it does the job. So let us calculate what we have to calculate here. Just copy pasting the right side. So here, this is just the definition. I mean, the quantity I want to calculate, and I want to show that this is equal to S0. Right, so that's nice. So this is R. Okay, and that's the first one. I can pull out S0. That's also fine. And I can plug in the definition of Q. That's right? So this is here u. So this is the first term. Now this is why I calculated 1 minus q. Well, this is just u r divided by ud multiplied with d. All right, it's nice. So how can we simplify this term here? That's nice. So these ud plus ud, they cancel. So what we have here is, this is, well, this come from these two terms. And then we have r minus multiplied with u minus r multiplied with d. Right. And now these r's are canceling, these the first term are all canceling. So what left is a zero. All right, that's exactly what we wanted to have. So u is doing the job. All right. Now last property is, okay, if I have such a q, the market is arbitrage free. So again, what would you want to check? So we want to check if we have a q such that S0 is given by the expected value of S1 divided by R, then the market is arbitrage free. All right. So let's, okay. Oh, sorry. I want to show that the market is arbitrage free. So let's take a trading strategy. So we want to show that there can't be an arbitrage opportunity. So we take a trading strategy. Okay, here it's just a constant. So that's phi to constant beta and alpha. And we take them away because if we want to have an arbitrage opportunity, it has to fulfill that the initial value is less or equal to 0. And terminal value is not as strict, almost surely non-negative, right? So this is what we have to fulfill. And this always exists by taking 0. So the 0 trading strategy. But now to have an arbitrage, we need that with a positive probability, the terminal value is strictly positive. So what we want to show is that this cannot be the case, because then there can't be an arbitrage opportunity. All right. So now I can't write anymore. Sorry, this was some IT issues. All right. So what do we observe? I mean, if we have such a Q, I mean, this is the assumption. So assume exist Q with right that S0 i.e. being equal to U is equal to Q, such that right this is S0 is indeed the expected value of S1 divided by R. So what do we want to consider now is, well, we take this Q, we consider the value process at time 1 divided by R, right? Which is by assumption strictly non-negative, right? This is how we constructed it or assume that we have such a trading strategy. Now we calculate this one, right? And this is the case that, I mean, the first probability that, I mean, if you go up with the probability Q, this is the value process at time 1. Well, it's 1 minus the probability that we will go down. So we have here D, alpha times DSU. All right. And now we can see what this is. So what do we have here? Let's consider the first two terms here. So that's R, the R's are canceling. So we have Q times beta plus 1 minus Q times beta. So that's just beta. Plus, right, so we have, and this is, okay. So that's alpha times, right? So you pull out the alpha and then you have exactly the conditional expectation. So this is the property 3i, which turns these two terms into S0. And this is nothing else than the value process of phi at time 0, which was assumed to be negative, or less than or equal than 0. All right. All right. So this means, since it's a non-negative random variable, which expectation 0, this is almost surely equal to 0. And this means here, I mean, this is exists no arbitrage on STS0. All right. Right. So if we take any trading strategy which starts with this non-negative initial capital, non-positive initial capital, and almost surely ensures a non-negative payoff at the end, well, then it has to be at the end always 0. Okay. So that's finished our proof. So we know now under which condition the binomial model is arbitrage free. Namely, if our parameters fulfill the second condition here, so that U is strictly bigger than R plus 1, strictly bigger than U. Right? Just to make it, I mean, clear or picture why this is actually what one would expect, right? So we start somewhere, let's say at 1. So let's normalize this here. So this is time 0. we normalize this here to 1, which is corresponds to the B1. So that we mean, okay, if we put our money into the bank account, what do we get? We get 1 plus R. Now this is risk-free at time 1. And this should be not better or worse than putting it into the risk key asset, where we get either D, either U or D, right? So meaning, okay, we have more, we can make more money, but we have to have the risk that we make less money. So this is geometrically why these parameters lead to a arbitrage free market. Okay, that's nice. So now we have ensured how we can, or understood how we can make the market, the binomial model to be arbitrage free. So we assume now that the binomial model BS is arbitrage free. Yeah. Okay. And well, let's assume this, and let's come to our second goal for today. Namely, how can we now price and hedge an option in this market? Okay. So this is pricing. And well, let's replicating an option. An option, I mean, we have seen is just a function acting on the underlying price here at time 1, because we have only one future time step. And here, this is just f is just a deterministic function from R to R. Right. Okay, what are the examples we have seen? Well, just so standard ones are the put and call options. This is call option, or the put option, which we have discussed before. Minus, which is the put option. So just that you have the examples in mind, but here, I mean, we consider a general option, since the only randomness here in the market is coming from S1. I mean, all the options look like this. Okay, so how can we find a reasonable or fair price of such an option, and why do we believe that this might be possible? Well, the belief that we might be able to do this is because the payoff of the option is determined by the underlying market, here by S1. So we have the hope that, well, also the prices are determined by this underlying market. So let us make a naive approach. And we will be lucky that this approach here works. And our approach here is, what we want to try is we want to try to replicate, so find a way to reproduce the payoff of this option by trading in the underlying market. And then if we find a way that we can do this, and we know how much money we need to do this, then the law of one price will tell us which is the price of this option, right? So if there are two ways to get the same payoff, they need to have the same price by the law of one price, because we have our no arbitrage principles. All right, so the approach we want to do here is we want to reproduce, or here replicate, payoff of the option f of 1 by trading the assets right. That's our financial market. Okay, so this is the meter idea, what we are going to do, and now we make this mathematically precise. So what does it mean? So we are looking, right? We're looking for initial capital. So this is the money we need at the beginning, so at time 0, which is just usually noted by V0 phi, and a self-financing trading strategy. Which is, in this context, as we discussed, it's just pair of two constants. So here, beta and alpha, which are assumed to be in RD. So what does this, trading strategy should fulfill? It should replicate, so it should reproduce the payoff. First, we start with the initial capital. So we allowed at time 0 to split up the capital V0 into two positions, into one in the bond market, so in the bank account, and the other one in the risky asset. Right. So this is, we split up our capital into these two positions. And now, so this is at time 0. And at time 1, what do we want to have? Well, we wanted to have to replicate it, so to reproduce the payoff of the option. So what we want here is that if we consider, so if our omega is equal to u, well, these, what is the value we have at time 0 if u equal to omega equal to u appears on the market? Well, the price went up, so this is what we get from having something in the bank account, and this is something, well, what we have holding from in the risky asset. Now we want that this here is equal to the payoff at time S1. So if this, this price on the market appears. Right. And the second thing is, well, let's assume the prices are going down. So what do we have? So the prices are going down. We want that this also replicate the option. So we want to match the payoff of the option. And this is this. Right? Okay, this is what we want to have. And this is actually rather nice, because what we see is here we have 3 linear equalities. And we have 3 unknowns, right? So we are looking for initial capital plus alpha and beta. And we have 3 equations. So linear algebra tells us we can solve this system. And I'm not doing the calculation, so I believe that all of you can solve a system of 3 equations to get the unknown parameters out of it. So please check, but I will just give you here the result. So alpha, if I haven't done anything wrong, is given here by this quantity. And beta is given by this. Divided by R. And last thing is the initial capital, well, is given by label this as well. Right. And to ensure that you really do this calculation here, we put a very similar question with on the next exercise or problem sheets, where you're allowed to or invited to do derive the similar replicating trading strategy in the case that the binomial model pays dividend. And then you can recover this formula by setting the dividend to 0. Okay. So, all right. Okay. Right. So what was the main point here? Well, the point is that we can find a way to, so no. We found initial capital plus a trading strategy phi alpha such that the terminal payoff of this trading strategy equals to the terminal payoff of the financial derivative f acting on S1. Right. So we have 2 ways now to get the same payoff. And we know the price of this. So to implement this trading strategy, so we do implement this trading strategy phi, we need the initial capital f v0 phi. So this has, I mean, the price for this trading strategy, for this payoff V1 phi is price is exactly V, right? Because this is the money we needed to implement this payoff. And now we can apply the law of one price, which we have seen in lemma 1.6, which tells us, well, the price of the option, so that's the price of the option, price of here, the option F acting at the price at time 1 is equal to V0. Right. So the moment we can find a replicating trading strategy for an option, we know the price, because we want that the market respects our no arbitrage principle. So here we are. And here in this simple binomial model with one trading strategy, we were able to find basically for any option such a trading strategy, such a replicating trading strategy. Okay, so let me put this into a corollary for later references. So corollary 3.8. So let us consider here the binomial model as we have done, and we need to ensure that it's arbitrage free. Binomial model. And let one, where this is a European option, Of course, F is here just the real number. So this is just the setting we just have considered. Have to be of course, this has to be measurable. So this has to be a measurable function, otherwise okay. Function. Then the price P of Fs1 of the option Fs is right. Okay, let's write it out. This is just the formula we just have derived. And okay. I mean, we'll talk about this formula in a second, and then we see that this is, I mean, might look long, but in the end we can write it very nicely in a much shorter way. And so we found the price, and even more, we found replicating trading strategy. Phi equal to Peter Oliver, which were given by 3.3, right? So I'm not repeating this here. So this here is just, yeah. Right, so this is our replicating trading strategy of an option in the binomial model with one step. And well, this here is the price. Okay, so there's nothing left to prove because we have derived it already. Okay, but, and this is what I promised you at the beginning of the lecture, is that we can actually make very nice observation. I mean, so this is the remark 3.9, which is a very important remark here. So first thing we want to remark, if you look at this formula, is, okay, if we recall our probability measure Q, which were given by this Q defined as R minus D divided by U. Right? So this is the probability measure which we found in this characterization of the arbitrage freeness of the binomial model, right? So this is here in number 3.7, the last property. Okay, so that's the measure. And now what we see here is, if we take this one, well, F0, right? Well, let me. So the price of the option right? So if we come back to the price of the option, which we have derived, well, now we can take this formula and rewrite it a bit. So we pull out the 1 over R. So that's what we do here. Now we plug in the definition of Q. So we get Q of F going up, right? Plus 1 minus Q. We put together the terms we have for the in front of the U going, the price process going down. Right? So that's it. And now this is a much nicer formula here. So the price of the option F acting on the price at time 1 is just given by the condition as when the expected value with respect to Q of the option actually discounted with the risk-free asset. Right? Let's make it red. First observation we make here. Price of an option can be computed as discounted expectation with respect to Q. But in general, not P, right? So just to clarify it, because it's a often appearing mistake in exams, don't use the measure P to calculate the price of an option. So this is wrong if you take here the measure P. At least in general. Right? I mean, there are cases, of course, that the measure Q and measure P coincide, and then, of course, it's correct. But in general, this is just wrong. Okay. Okay, let me, since I promised this, do you understand where the measure Q is coming from? Well, if you take F to be this to a second remark. So if you take now F to be the identity function, all right? And we'll label this. And we apply, let's say, star. What do we get? The price of S1. Well, we know the price of S1. The price of S1 is S0. Is equal to what? We apply this formula, so this is equal to the expected value under Q of S1 divided by R. This is nothing else. Well, the expected value of S1 divided by B1. Right? And here we are lucky this is nothing else than S0 divided by B1, because, well, this here is just 1. Okay. And now you see, I mean, iterating the calculation we have done before for this special option here, so F being the identity function, you immediately get out the Q, which I just gave you in the proof of lemma 3.7. Okay, what's the message here is, or the observation, the discounted price process. What is it? That's S divided by B is Martingale under the measure Q. Okay. All right. So this is why we call this measure Q the equivalent Martingale measure, because it's also equivalent to the measure P. So just to so the Q is called equivalent Martingale measure. We will study this in more depth in the next lecture. So that's here a definition, which we also like formulate in a more general context next time. Since BT is a martingale under Q, and Q and P are equivalent. All right, so since equivalent measures, to recall it, means that they have the same null sets. Since Q and P here, both assigns the elements U and D positive probabilities, well, the null sets are the same. All right. So these are the two take-home messages from today. Wait. Here, right, this is first one, and this is the second one. Okay, we have 10 minutes left, so we can start with the next chapter. And this is what we want to understand now better in a more general context is, how no arbitrage and this notion of martingale measures relate. That's 3.3. No arbitrage and martingale measures. Okay. In order to understand this better, what we see is not the price process itself as a martingale, it's the discounted price process with this, which is the martingale. So we want now to introduce all the discounted quantities because these seem to be the right objects we want to work with. And then we want to understand how these martingale measures appears in the context of no arbitrage or arbitrage. Okay. So what we want to do now again is to consider a general market. So we leave the framework of the binomial model for a moment, and we will come back to it later. So we consider a general financial market, and this might have again more than one trading period. So it's a general framework we have already introduced last time, which is our market B and S over an index set T. So discrete time financial market. And we introduce the discounted price process. Which is labeled by S tilde, which is again, of course, I mean, it's 1, 2. So these are D prices, and they're discounted by the risk-free asset. Which is defined by right, so S tilde 1, S tilde I, so the I risky asset time T is just the price of the ETH asset at time T discounted by BT. It's called T and T, and we have D asset, so I can be a number between 1 and D. Okay. All right. So that's this is the definition of the discounted price process here. And that's right here. Right. Right. So, and to make my life easier, let me also introduce the difference operator. So this means delta S tilde T is S tilde at time T minus S tilde at time T minus 1. Right. So this is the price movement of the discounted price in the T trading period. Okay. All right. So this is okay. We want to go over from undiscounted quantities to discounted quantities. So we want to somehow to understand how the object we introduced behaves now under the notion of discounting. And this is, if we start in the next lemma, so this is 310. Which tells us what? Let us consider a self-financing trading strategy. Here now, general context. So this is a predictable process. Alpha, beta and alpha. And then we have that if we consider the discounted value process, so consider the value process associated to this trading strategy, and I discount it as well by the risk-free asset. Well, and then the value at time B0, so the initial capital, so the discounted value process here is given by the initial capital plus the gains losses we make by trading in each period in the discounted price process, right? Or just to, right. Okay. All right. So we start next time with the proof. And let me stop here now because I hope I was not too fast today. There. And well, I hope you all enjoyed the lecture, and well, thank you very much for watching the video.